Welcome to Calculus with Power series. So the idea here is basically we have a series. We essentially have a function, right? So we have a function f of x equals a sum from n equals 0 to infinity of a sub n times x minus c raised to the n, which we know exists sort of in its radius of convergence, right? So, which we know converges is defined, right? So converges on at least the interval from c minus r to c plus r. The question is this function continuous? Can we take its derivative, etc.? Can we take its integral? So the question is this function continuous? Can we take its derivative? And can we integrate it? And the answer is yes. So for a power series, the sum from n equals 0 to infinity of a sub n times x minus c to the n with radius of convergence r. Oh, let's make this a f equals. So for a power series, f of x equals that sum with radius of convergence r. We have that f is continuous and differentiable. On that little domain, at least within the radius of convergence. So continuous and differentiable on the interval from c minus r to c plus r, the open interval. F prime of x is the sum from n equals 1 to infinity of a sub n times times n times x minus c to the n minus 1. So we just take the derivative one term at a time, right? We would have the power rule, chain rule would just give us a times 1. And this has radius of convergence r, as does the integral. So the integral of f of x dx, the indefinite integral, is some constant c plus the sum from n equals 0 to infinity of a sub n over n plus 1 times x minus c to the n plus 1. So here we can differentiate term by term. We can integrate term by term. And both of these also have radius of convergence r. So again, we can take the derivative term by term. We can take the integral term by term. This comes in handy. So for example, let's consider the function that we were working with in the previous video. F of x is equal to the sum from n equals 0 to infinity of -2 to the n. And let's make this the one that we switched to. So -2 to the n times x plus 1 raised to the n, which was defined on -1.5 to -0.5. Our job is to find the derivative and the integral. So if f of x is equal to the sum from n equals 0 to infinity of -2 to the n times x plus 1 to the n, we have the derivative f prime of x is simply the sum from n equals 1 to infinity, right? The 0th term, that n equals 0, is just a constant, so it disappears. So it's only the n equals 1 term that and beyond that will stay. That -2 to the n is simply a constant. It comes along for the ride. Derivative of x plus 1 raised to the n is n times x plus 1 raised to the n minus 1. We also have that the integral of f of x dx is equal to the constant c plus the sum from n equals 0 to infinity of, we take our -2 to the n, that again is just a constant along for the ride. We integrate x plus 1 to the n. We would have to divide by n plus 1. And we would then take x plus 1 up to the n plus first. So that was our backwards power rule, right, from earlier in the semester. So these are our derivatives and integrals. Okay. So just a quick note. Note that f of x here is the sum from n equals 0 to infinity of -2 to the n times x plus 1 raised to the n. We could rewrite this as the sum from n equals 0 to infinity of -2 times x plus 1 and then that whole thing raised to the n is just a geometric series. And so this is a geometric series with our lowercase r being -2 times x plus 1. And so we know, therefore, that our series converges to 1 over 1 minus r. Right? Our leading coefficient here is just a sub 0 is just 1. So we have our 1 over 1 minus r. And that is therefore 1 over 1 plus 2 times x plus 1. Or in other words, 1 over 2x plus 3. Right? So what we have then is that the sum, so our f of x is just 1 over 2x plus 3. Right? So we have then that our integral of f of x dx is simply an integral of 1 over 2x plus 3 dx. And that would be just 1/2 times the natural log of the absolute value of 2x plus 3. And then we'd have some constant C1. So, but we saw that the integral of f was also just some constant plus another series, right? So, but the integral of f of x dx was equal to some constant c plus the sum from n equals 0 to infinity of we had -2 raised to the n times x plus 1 to the n plus 1 all over n plus 1. And so what this means is that c plus the sum from n equals 0 to infinity of -2 to the n times x plus 1 raised to the n plus 1 over n plus 1 should be equal to 1/2 times the natural log of the absolute value of 2x plus 3 plus C1. Now, if we plug in x equals -1, then we have C plus, plugging in x equals -1, that's just going to be 0 raised to any power. We'll have a 0 to the first power at n equals 0 and 0 beyond that for higher n. So the sum will just go to 0. Why don't we actually write that out? So I'll have the sum from n equals 0 to infinity of -2 to the n times 0 to the n plus 1 over n plus 1. So that part will just go to 0. This is equal to the 1/2 times the natural log of, we would have -2 plus 3, or 1, and then plus C1. So this is just C plus 0 is equal to, natural log of 1 is 0, so 0 plus C1. So we have our C and C1 are equal to each other. And so we wind up getting that 1/2 times the natural log of the absolute value of 2x plus 3 can be written as the series, the sum from n equals 0 to infinity of -2 to the n over n plus 1 times x plus 1 to the n plus 1. So this is kind of an interesting trick that we have available to us. If we recognize the original series as one we know, in particular a geometric series, we can actually figure out what that series is as a standard function. We can integrate the standard function, and we come up with another series for a completely different function. So this is just some techniques we can do with series using some calculus. In the next video, we'll actually do a little preview for differential equations and how series can be useful in differential equations.